In this video, we're going to talk about a new way of making alcohols. Let's first review an old way, the acid-catalyzed addition of water. How does it work? The double bond gets protonated, you form the most stable carbocation, the water attacks, it loses a proton, you make your alcohol. This gives you the secondary alcohol. But what if you really wanted the primary alcohol? How could you reverse the polarity of everything here in order to form the opposite regiochemistry? Well, what you need is something which, instead of being H+, is going to be H-. And it turns out we have something like that. Let me load a different structure here. If we use the reagent BH3, boron is a Lewis acid, H is H-. BH3 in solution actually has to have a good solvent like THF, and the THF helps stabilize that boron by coordinating to the empty p orbital. Because without that, it essentially would be a very reactive 6-electron species. Mechanistically, we usually drop the THF and just draw it as BH3, but you should always remember it starts off bound to a THF. So how does the reaction work? Well, the double bond attacks the acidic center, just like it does if it was a proton. And what do you get? Well, you get the acid on the primary carbon. And so let's draw that out. So in this case, the acid is BH3. So we're going to make the carbocation again. Again, it's secondary, but attached to that first carbon is the boron with its 3 hydrogens. So here's the boron. It still has the 3 hydrogens. Okay, and we draw one up, one down, one out here. And of course, it has a negative charge. So what happens next? Well, we have this hydride here, H-, very near to this positive charge. Not surprisingly, it just moves. So we take an arrow and we simply show the hydride leaving the boron, going to the positive charge. And we draw that out, okay, it's going to essentially be a compound where we've added BH across the double bond. So let me draw this out. And it essentially get rid of the negative charge, get rid of the positive charge here, and I get rid of one of those hydrides. I guess I moved the one up there so I can draw it like this. Well, this is the product. It's a borane. It's an alkyl borane. Now, these alkyl boranes still have BH bonds. So what happens here is that this molecule will just keep on going. It'll react with another mole of the starting material, okay, and do the reaction again, and then it'll do it again. It'll just keep going. It'll do it twice more because it has 2 extra hydrogens. So when it's done, you'll have the boron down here, okay, and the boron will be a trialkyl borane. It'll be a trialkyl borane bound to 3, in this case, propyl groups. And here we are. We've got 3 propyl groups on there. So this is a trialkyl borane. Now, these trialkyl boranes are not what we wanted. What we wanted is the alcohol. So it turns out that these things can decompose, okay? And the way they decompose, let me center this a little bit, get a little more room, is you hit them with hydrogen peroxide and base. So hydrogen peroxide and base. Well, hydrogen peroxide, of course, is HOOH, H-O-O-H, but in the presence of hydroxide, which it is, since we have a hydroxide around here, some of that peroxide will get deprotonated and it'll form the anion of hydrogen peroxide. Well, this anion of hydrogen peroxide will attack the boron because the boron still only got 6 electrons. So it'll attack like yay, okay, and will form this new complex, okay, which has now got an oxygen, hydrogen peroxide bound to that boron, and the negative charge is now back on the boron. So what happens now? Well, the next thing that happens is that the alkyl group does a migration to the oxygen, which looks really, really weird, but it can do that, and it can break this really weak OO bond. These peroxide bonds are so reactive because, well, OO bond is weak. So we do another kind of migration where the alkyl group leaves the boron, goes to the oxygen, and we kick out the hydroxide like this. Let me draw that a little bit better. So this alkyl group moves over, and that's going to give us, again, I better get a little bit more room here. That's going to give us a compound now, which it looks a bit like the original one over here, except now one of those bonds now is got an oxygen in there. And so we've inserted an oxygen into the boron-carbon bond of one of these. And what happens, of course, is that just happens 3 more times. So we end up making the compound, which is where am I going down here? I'm running out of space. Again, let me move things around. So we end up making the compound which has 3 of these alkoxy groups. Come on, having trouble drawing this. 3 of these alkoxy groups bound to the boron. Now this guy then, if you just treat it with water, okay, will fall apart and form the 3 alcohols and boric acid. So boric acid is simply this compound, and you'll get then your 3 moles of the alcohol from one of those compounds. So the net effect is that you've started the propane up here, you've turned it into the primary alcohol. So this seems very roundabout, but is very, very useful because it means that you can make those primary alcohols. And often primary alcohols are much more useful than secondary alcohols. So this is a really good reaction. And in general, we simply say when we do hydroboration, the reaction gives you the opposite isomer than you would get if you were doing acid catalyzed addition of water. The other thing that's nice about hydroboration is that you don't have to worry about rearrangements. And the reason is that these carbocations don't exist for any appreciable time because that hydride adds essentially as quickly as the boron adds. And so you don't have rearrangements in these hydroboration reactions. So it's a really nice reaction for doing synthesis.